Hello everyone, I'm Vasita Das, currently a PhD student in Professor Thomas Critchard's book at Forschung Centrum Jülich. Today I'll be talking about the effects of doping on the efficiency of perovskite solar cells. Some recent publications have shown that doping or photodoping might lead to improved solar cells performance in perovskites, and we want to understand the physics behind it. The general understanding is that doping of material will lead to the decrease of the radiative lifetime, and hence the total recombination would be increasingly dominated by the radiative process. As a result of this dominance, the luminescence quantum efficiency would increase as shown in this figure over here. What we want to understand is that does this increase in luminescence quantum efficiency really ensures that the performance or the efficiency of the solar cell will also increase? Uh, this is primarily because the diffusion length will actually decrease, because as the radiative lifetime decreases and the effective lifetime is dominated by it, the diffusion length would also decrease because it is directly proportional to the radiative lifetime or the effective lifetime of the material. But also in perovskite solar cells, due to poor mobility or the low mobility of the transport layers, there's a lot of poor charge extraction or charge accumulation inside the device, and this may lead to higher recombination. So we want to answer all these questions of how doping would in in the end play out in the uh, in increasing or decreasing the performance of the perovskite solar cells. So first we studied the effect of doping on the effective lifetime of the device and the open circuit voltage. What we saw is that the effective lifetime decreases as we go on increasing the doping density, because the radiative lifetime actually also decreases, and towards very high doping densities it is completely dominated by the radiative lifetime. As a result of this decrease of the effective lifetime, we see an increase in the open circuit voltage and towards the radiatively limited open circuit. What we also saw that the mobility of the transport layer does not affect the VOC at all, because at VOC we basically have flat formula levels everywhere. Now, secondly, we studied the effect of doping on the total recombination inside the device and the short circuit current. So at short circuit, we see that with increase of doping density, the total recombination rate actually increases. And this increase is not only due to the radiative recombination, but also the SRH recombination or the non-radiative recombination also increases, and thus increasing the total recombination inside the device. As a result of this increased recombination, we see that the short circuit current actually decreases. And what we also saw that if we decrease the mobility of the transport layers, the recombination increases further and the short circuit current decreases further. So in the end, as a result of this charge accumulation inside the device due to poor transport layer mobilities and probably the decrease of the diffusion length, what we see is that the efficiency also decreases as a result of this decrease of short circuit current as well as fill factor. So away from the VOC, we do not have flat Fermi levels, and there is a lot of charge accumulation inside the device, which leads to more and more recombination inside the device, and thus the efficiency falls rapidly. So the answer to our question was that the increase of internal quantum efficiency alone does not ensure that we would have a better device with doping. Thank you.